All right, today we're putting on our detective hats, our microbial detective hats, that is. Our mission? To track down a microscopic culprit that's responsible for millions of illnesses every single year. We're cracking the case of Salmonella.
You ever get hit with a nasty bout of food poisoning and just wonder, what is actually happening behind the scenes? What goes on in a lab to pinpoint the tiny villain that made you so sick? Well, today we're going to follow the investigation.
Okay, so every good investigation starts with a case file, right? Our patient is presenting with a fever and diarrhea. The initial report says they recently ate some undercooked chicken, but they also have a pet turtle. These are our very first clues, and they're already pointing us toward a pretty likely suspect. So, with that initial report, it's off to the lab. This is where the real detective work kicks off, where we move from just symptoms to actual hard evidence.
And you know the first thing we've got to do? Get our eyes on the suspect. It's time to head to the microscope.
And there it is. Under the scope, we see these little pink rod-shaped things. Now, in lab speak, we'd call this a gram-negative bacillus. And get this, they're moving. They can actually swim around. The profile is starting to build, but we're going to need a lot more evidence.
Okay, next up is something called the Mac-Conkey-Agar test. The best way to think about this is like a super selective cafeteria for germs. It's designed to see if our suspect likes to eat a sugar called lactose. Salmonella? It's a really picky eater. It can't digest lactose, so its little colonies stay colorless. This is a huge clue that helps us cross a bunch of other bacteria off our list of suspects. All right, we've got a visual description, but that's not enough. We need a confession. It's time for the key interrogation, where we basically force this bacteria to spill its deepest, darkest secrets.
And our main interrogation tool? It's called the triple sugar iron test, or TSI for short. And let me tell you, when it comes to nailing Salmonella, this is the absolute smoking gun. So, you're probably wondering, how does this interrogation actually work? Well, we take the bacteria and literally stab it into this special gel in a tube. This gel has 3 different kinds of sugar plus iron. And based on the crazy color changes and byproducts that show up, we can figure out exactly how it eats and, maybe most importantly, if it produces certain kinds of gas. And here it is, the moment of truth. Look at that. That dramatic black stuff forming at the bottom of the tube? That is the telltale sign we've been waiting for. It means our little bacterium is producing hydrogen sulfide, or H2S. This one clue, man, this is a massive leap forward in our case. Okay, so we've got our key pieces of evidence locked in. Now it's time for the classic police lineup, comparing our evidence against the usual suspects to get a positive ID. So let's take a look at our lineup here. We know our guy produces H2S, and we know it's motile, it can move. Right off the bat, Shigella is out. See? It doesn't do either of those things. Now, Edward Celia, it looks pretty similar, but there's a key difference in something called the indole test. That test checks for a specific byproduct, and it sets them apart. All the evidence is pointing hard at one name. And really, it all comes down to this simple formula right here. H2S positive, plus motile, plus indole negative. There's only one culprit that fits that description: Salmonella. The evidence is overwhelming.
And just to be 100% sure, we run a couple more quick checks. We already know it's motile, which rules out Shigella again. And it's urease negative, meaning it can't break down urea, and that rules out another lookalike called Proteus. Yep, we've got our guy. It's Salmonella.
Okay, so we've caught the criminal, we've identified it, but that's only half the story, right? Now we need to figure out its MO, its attack plan. How does Salmonella actually do its dirty work? Here's the key thing you need to understand about Salmonella. It is invasive. See, a lot of gut bacteria are happy to just, hang out in your intestines. Not Salmonella. It's not content to just stay put. It actively breaks into your body's own cells to survive and multiply. That's its whole game plan. So, here's a step-by-step of the invasion. First, it hones in on these specific cells in your gut lining, called M cells, and busts its way in. Then, and this is a really clever move, it actually lets itself get eaten by your immune cells, these things called macrophages. But instead of being destroyed, it just survives inside them. It uses them as a hiding place to multiply. And as you can imagine, this sets off some major alarm bells in your immune system. And oh boy, does that alarm trigger a counterattack. Your immune system spots a part of the bacteria's outer layer, and that kicks off a huge chain reaction. Your body just unleashes a flood of these inflammatory signals, basically calling in the cavalry, an army of immune cells called neutrophils to rush to the scene of the invasion. And this is probably the most important takeaway of all. The fever, the cramps, the misery. A lot of the symptoms that make you feel so terrible when you have salmonella, they're not directly from the bacteria itself. They're actually caused by your own body's incredibly fierce but totally necessary immune response, trying to fight off this tiny invader.
So, think about what we just did. We went from some pretty general symptoms, followed the clues in the lab, and pinned down not just the culprit, but exactly how it operates, which leaves us with a big question. Now that we know in such detail how this microscopic criminal gets caught, how can we use this kind of detective work to stop the next outbreak before it even starts?